Okay, so we will talk to you all about texture compression. That's what we do. So who are we? We are co-founders of Binomial. It's a small startup. We used to work in games. So I worked at Oculus building virtual reality demos, and Rich worked at Valve and Microsoft. And before that, I worked at Unity, helping them build their game engine. We actually, after working at a bunch of game companies, we founded a consulting company together. We helped launch Intel's Project Alloy headset. We did a lot of virtual reality consulting. But overall, we're kind of optimization experts, so we help people with those kinds of problems. And eventually, that road led us into starting a texture compression company because we found one of the #1 concerns we always ran into was textures are too big. They are causing a lot of the bottlenecks, especially in the virtual reality space. And we did all of this in C++. So that's why we're here. So the main point of this talk is to talk about Basis. That is our texture compression product. That's what we're working on. And then we'll go into a little bit about C++, dive into some technical details, especially for those unfamiliar with GPUs or who want to know the innards of GPU formats and how all this works. We'll show some benchmarks to show that we're not making this up. And then we'll talk a little bit about what the future is. So in short, Basis makes images smaller on your computer. It makes them take up less space, and that's the core of it. People always tell me I need like some sort of video for our product, but it's just making an image smaller, so it's not the easiest thing to describe to people.
It's hard to describe in an elevator too.
But this is foundational. Images are everywhere, so it's a really important piece of software in a lot of applications. And the most important part of Basis is it actually is compressed on the GPU. Believe it or not, it's the only image format that has similar size to JPEG that is compressed on the GPU. We work really hard at that, and we think it's so important that we're actually donating this file format to the Khronos Group and making it an open standard so that anyone can target it, anyone can transcode. We're working with hardware vendors to get it in hardware and browser support. We're hoping that essentially in 5 to 10 years, this will be the image format you use in a lot of applications. So why is it important? I went into that a little bit to give you an idea of how much texture data is out there. For instance, in games, it's easily 70 to 80% of the application. So think about reducing that size. We can cut a lot of games texture data in half. We'll take questions at the end, promise. And for a lot of applications, Basis is just a necessity. It's just needed. Because they can't run their application. It's too big without more texture compression. So we're really excited about innovation that'll open up too. So I figured talk a little bit about how we came to this point. Why is this only being solved now? GPUs have been out a very long time. Why didn't they fix this a long time ago? So Basis. So JPEG is actually really good for compression. JPEG is great in terms of CPU-side storage. It does a good job, but it's uncompressed on GPUs. It was invented before GPUs came out, and it didn't consider a lot of those concerns. So that's not good. GPU manufacturers tried to solve this problem. They made their own GPU formats with hardware acceleration that worked great on GPUs, but the problem is they were pretty big on CPUs. And it was a fragmented ecosystem, as I'm sure you all are familiar with, can happen. They all released their own, and it didn't work on their competitor's GPU, and it was a little bit of a mess. So that actually wasn't a good solution. So we like the size of JPEG. We want to maintain a small size CPU size. We like its multi-platform nature. A lot of web applications still rely on it. But we like the size of the GPU format, so we have solved these problems. We have a similar size to JPEG on the CPU. It can be multi-platform, and it transcodes quickly to the GPU format you need. So it utilizes existing hardware acceleration. So there's 3 parts. There's the encoder. If you only care about one GPU format, which is true of a lot of games, we can target just that one GPU format, and you add lossless compression to it, and it sticks right into existing pipelines. But if you are, say, a web application and you need it to be multi-platform, we have a multi-platform solution. We created our own file format, .basis. You compress to that, and then at runtime, you transcode to the format you need. So next,
okay.
C++.
My name's Rich. I met Stephanie, it must have been almost 2 years ago, and I was at Unity at the time, and she was at Unity. So we got talking a lot, and the kind of history behind this whole thing is we had an open source library named Crunch, or I did, and I just open sourced it while I was at Valve, and I was busy on other things, and I didn't have time to really to do much with it. I just put it out on GitHub and just let it go. And my first big customer was Google, on Google Maps. And I'm like, wow, there's something important here, And then other developers started using it. More and more game developers would contact me, and a lot wouldn't contact me, and they would sneak the information to me through back channels, like what's going on. So that's why we chose Basis to work on as our first product. We were doing contracts last year, and we really thought, like, we want a product, we need a product, because contract work is just linear, like you only create income linearly, but a product can result in exponential income. So this is what we've been working on, and Crunch was written in C++, and so is Basis. I'm using C++ since 96, 95. All the projects I've worked on pretty much in the last year and a half, all of them have been C++. They've been a wide variety though, mostly 03 to be honest, just a little sprinkling of 11 and a little bit of C++. I think it's called OX from Microsoft. Anyway, we don't use all features. Like, I come from a game development background, and we're really concerned about performance in games. Like, maybe paranoid about it. We are paranoid, what am I saying? And we don't trust a lot of stuff. And plus, we want to ship across a wide range of platforms without worrying about the standard library implementation on each platform. So just like most game developers, I usually just reinvent everything myself for the project, specifically things like containers and stuff like that. I like to know exactly what everything is doing. So I use the compiler, I use OpenMP, and we use our own containers. There's a few things in C++ and 11 that are interesting, but to be honest, like we're working in a hard problem domain right now in terms of performance, and we're slowly, transitioning to it. So the reason why we care about performance is because Crunch was incredibly slow. It would take 1 minute to 2 minutes per image. Clients would have to compress thousands and thousands of, hundreds of thousands, some of them. So they have to deploy it in the cloud. And for a product, that just kind of is unacceptable. So we're down now to about 20 seconds for a 2K texture on a laptop. And that, thankfully, all the compilers that we target have great support for OpenMP. So I'm really a huge fan of that now. But we also like C++ because it gives us access. It's basically a sweet spot. I programmed in C a long time, and that felt like a high-level assembly. And C++ gives us this wide range of this whole abstraction spectrum. We can go all the way down to intrinsics, or we can go all the way up to these higher-level primitives. And that is incredibly powerful. And every time I go to some other language and I mess around with it and play around with it, I just miss that. I like that abstraction hierarchy. Anyway, we kind of covered this. This is why we care so much about performance. So basically, encoding time is money. So if a client has to deploy our encoder in the cloud, like on Amazon EC2 or something like that, it costs money. And so for us, every ounce of performance we can get out of our encoder results in less money for our customers. And on the other side, on the decompression or transcoding side, we are competing against some of the fastest lossless decompressors in the world, written by some amazing programmers in C. So for us to have a competitive product, it has to be really fast. And so what we generally do is our transcoder is a header file library. This is something I first saw some people at Rad Game Tools do up the road. And header file libraries are these neat little things where it's just typically one header file that contains all the code you need. So all the application developer has to do is include that one file and, in theory, not worry about it. And so that's what we also try to do too. We put everything in one header file and just ship people that, and they can cross-compile that with EM scripting, which is another incredible piece of technology that can take C++ code and cross-compile it into JavaScript. And I'm by no means an expert on this tech, but That's how Google was able to deploy Crunch in their infrastructure. So I just wrote something in C++, and then they just deployed it in JavaScript through some kind of magic, and it was amazing.
Yeah, it is pretty amazing. I think our end goal is to have browser support and not have to force people to do the transcoding step in JavaScript. But believe it or not, JavaScript is actually fast enough. And that's because our transcoder is pretty simple. So for those unfamiliar, GPUs are basically why we exist to make texture compression on GPUs. So it's really important to our algorithms and to our business. They were created because graphics requires a lot of parallelization, and you really don't need a lot of memory for a lot of like the standard rendering going on. So graphics processing units were created. It has more limited memory, but it's okay for a lot of applications. And the really exciting part is now a lot of interest has been spawned in compute and general purpose GPU programming, which is awesome. So it's used in AI and machine learning and all these different applications that also like highly parallel algorithms that don't use a lot of memory. It's great, but because it's developing so fast and so exciting, it's also not as stable. So that's a big reason we are partnering with GPU vendors to try to get this transcoder taken care of by their drivers and their hardware, because they are on top of the cutting edge developments and what GPUs need.
Let me just add one thing to that. So the big problem on GPUs is bandwidth. So you have a ton of parallel threads all executing these little kernels of code, and they all want to fetch from texture data. And if you have to store 32-bit or 64-bit texture data, the amount of bandwidth is incredibly high. Mm-hmm. So the GPU vendors back in the late 90s developed a whole bunch of algorithms for dealing with this. And we're going to cover this a little later, but what it all boils down to is block compression. So the image or texture is divided up in these little blocks, and then they compress each block separately, and then there's specialized hardware on the chip to decode those blocks right from a texture cache. So in other words, like the stuff we're working on is inherently hardware decodable because it's in every GPU around.
Absolutely.
The problem is all the formats have not been standardized. So there's this huge variety of formats out between mobile and desktop.
People have tried very hard to do JPEG decoding on the GPU, but it just takes up too much memory and is not multi-threaded enough. It's not made for it.
And it's inherently not random accessible either.
And now there's GPU hardware decoding, which if something has hardware decoding, you should use it. So we focus on using block-based compression algorithms ourselves because at the end of the day, we're targeting these GPU formats, and that is the end goal. So basically, we try to be very smart in the encoder, and dot basis is a block-based format as well, but it's one that kind of unifies all the GPU formats, and then it's really easy and quick to transcode. So our algorithms are block-based as well. So thought just to inform everyone and kind of explore block-based compression algorithms, I figured I'd go through a few of the GPU ones that exist. They're kind of interesting. ETC1S covers all mobile devices except really old iOS. It's actually a really amazing format with a simple concept behind it. You split the image into blocks. You assign each block only one color, just one color per block.
The blocks are 4x4.
4x4. And each pixel within the block gets a grayscale value of that color. Now, when I first learned about this format, I was like, how can that work in practice? But it's because the human brain picks up on grayscale much more than color. So in practice, it's actually an extremely good format. We've made normal maps work in this. It's been surprisingly flexible and really good. And it's a topic for another talk, but the whole idea of perception of image quality is fascinating. There's no good algorithms. Like we use SSIM and PSNR, but there's no good algorithms to judge how high quality an image is. It's kind of fascinating. A lot of big tech companies, they just sit people in front of images and say, tell us how high quality this image is, because the human brain is really complex. DXT takes a different approach. It says, okay, forget grayscale. We want more color. We want color to play a bigger role here. So what they do is they take a line through 3D color space. You can kind of picture it. Each block gets 2 colors, and then you can choose where on the line you exist. So you can kind of see how that could potentially work. It's still limited, but now you can choose from a little more colors. It's actually a really hard format to encode to sometimes, because if you get the wrong endpoints, it can really mess things up. This is on desktop and consoles, not mobile. And so Basis, basically, there's lots more, by the way. Those are just two, and that's part of the problem. Basis looks at all these block-based formats and tries to unify them and tries to create one that can kind of transcode into all of them. We also are better on the CPU. Oops. So this is an idea of the mess we're dealing with. These are all the GPU formats. So there's high quality, there's lower quality, there's desktop and console and older iOS that we wish didn't exist, but we have to support it, and all these different formats, and this is why we're working on this. Our plans are, right now, we have individual encoders for ETC and DXT. As I said, a lot of game companies and AAA studios like those because they target one console. They don't target, your mobile phone as well and things like that.
And we've shipped these encoders to companies. So.
Netflix was one of our first customers using it, integrating it in their animations and videos. So, and right now we're in talks with pretty much so many companies.
It's ridiculous.
We're like on the edge of, since being standardized, everybody wants to use this technology.
Also just license their codec.
Yeah. We have a dot basis that just covers ETC1 in a production-ready state. We have the universal, but we want to make sure it's more solid before we release it. So end of 2017, we will cover all devices except older iOS devices, pre-A7.
And they're dying off. So.
Well, unfortunately, like in kids' games and other regions of the world, they're still there, but it's a complicated format, so it'll take some time. And immediately after that, we could support those older iOS devices. We could also go into high-quality formats. Those are really exciting. They're huge now, and we can make them a lot smaller. So I really want to do high quality personally. The goals are to have a completely multi-platform dot-basis solution that can essentially be a new standard for image compression in our industry. We are actively working with hardware vendors and browsers and getting support for this so that hopefully in however many years it takes, you will all have dot-basis hardware acceleration in your GPUs. And we will sell one encoder for that, but that will be the standard in the industry. So that's our goal, and that's what we're working on.
I just want to put this out there is we're open sourcing the transcoder, and we are writing a spec for it. Anybody can write an encoder for this. And so we've proven that we can do this already last year. So we are going to license the encoder, but anybody else could do their own encoder. So we're not like there's no lock-in on that.
No, like we are here because GPU formats are a mess. We don't want to create more messes at a higher abstraction.
Our goal is to unify them. We want to have the first unified GPU.
So it can be, you could say, oh, is it harder as a business if you're opening up your format? And I think it's actually good because then more people are using it. We'll provide one encoder that's ready to go. Other people are welcome to make their own. So Rich, standardization?
Sure. We've not practiced this at all, by the way. It's terrible. Yeah, we've kind of covered this. So the problem you have right now as a graphics engineer shipping a product on multiple platforms, if you're like making your own engine, or even if you're dealing with an existing engine, is there's this huge fractured ecosystem. And it's really bad because if you encode your texture to ETC, you'll get different artifacts than if you encode the DXT or ASTC or BC7. And the quality you'll get, say, with BC7, the range of quality there will be much higher than what you would get with, say, ETC. So it can be pretty nightmarish for a studio wanting to ship their content on all these platforms. They actually have to go and sometimes actually tweak the settings individually per art asset. So like we want to establish an existence proof that yes, this whole thing is unifiable. And part of the reason why the ecosystem fragmented like this is because of patents, because you had hardware company X patenting their format and then wanting to license that to all the other hardware companies, and so when Y and Z came with their own formats, and it's just a huge mess. And the open source world's tried to solve this, but the reality is all of the encoders have different bugs too. So it's a nightmare. It's like the dark ages. And I'm not sure if you're familiar with GPU coding and stuff like that. But this used to be a problem with shaders back in the day, the equivalent of programs for GPUs. And back in those days, you'd actually have to code in like this assembly-like language that's specific for each GPU, and they fixed that. They have higher level standardized languages like GLSL and HLSL, and so that's kind of what we're doing for textures. So anyway, we're official members of Khronos. For a tiny company like us, it's been actually an interesting experience. They've been really great to us. Have our logo up against with all these other companies is amazing. Another little note in there is that if you ever use Unity, our open source product, Crunch, is in Unity.
And so we're working with all these companies to integrate Basis into their tech, and it can take a lot of time, especially at the lower levels of the ecosystem. But we are working on this. And Khronos, for those who don't know, is a standards body. They create standards for the graphics industry.
So you heard of OpenGL? That's their thing.
Yeah, OpenGL, Vulkan. So benchmarks. As an example, we put this at kind of high quality settings just to see how much reduction do you get even when the image is really high quality, and it's significant. So the top one is just the GPU format by itself. The second one is trying to compress it with lossless compression, which doesn't work very well. And the third is using Basis, and it's much better.
It's just one tiny example, but we have some
more thorough
detailed
benchmarks.
Yeah. So what this is here is what we call a rate distortion graph. So at the bottom, we have the compressed size in bits per texel. And up and down, we have quality. The higher the quality, from 0.66 all the way to 1. 1 is perfect quality. And so like if you ever played in Photoshop or an image tool, like with the various JPEG quality settings, what you could do is you could try every quality setting and then measure how many bytes, or record how many bytes are actually output for the JPEG, and you make a little graph. That's what we're doing here. This is one of our older codecs that we shipped to Netflix earlier this year. And so what this is you can see all these data points on there, and you can see how the curve goes up. And then we have, and it's kind of hard for me to see, but there's 2 dots to the far right. And so at the very, very, very far right, at 4 bits per texel, you have quality level of 0.97 or whatever. That's the GPU format. That's the quality you'll get if you just code directly to the GPU format. And of course, it's all these GPU formats are in the general case lossy, but it's still pretty high quality. And then if you just take that and throw that at like gzip or zstandard or Brotli, whatever, you'll see that the bit rate has gone down, but of course the quality hasn't changed because it's a lossless codec. And that's I think the red dot there. And now you're going to see this curve. And the curve starts at quality level 0.94. So this version of the codec we ship wasn't able to achieve the entire rate distortion curve. To translate that to JPEG terminology, it was able to achieve like quality level 80. So it went from 80 to 50, for example. You can see as the quality levels turn down, as the quality goes downwards, the bit rate goes downwards. And so what we do is we run our encoder on thousands of images. We record these rate distortion curves, and then we optimize our codec.
We're constantly tweaking it. Like you can see in some of it. So in this one, another thing worth noting is low quality is usable. It's very, very usable. We have a lot of people that ship only using low quality because it's just good enough. The way we do artifacts when we do lower quality is very similar and mimics the GPU formats, and you can get away with it. So the low quality in this case is 1/8 of the size of the GPU format about. So it's huge reductions.
On the flip side, there are some customers that our newer codecs let you access almost the entire curve all the way up to the red dot. And what they do is they only dial the quality down a little tiny bit. And when they do that, they can still cut the amount of data they ship to their customers in about half, which is a huge amount of value. So you can see like the curves all differ depending on the texture. Unfortunately, we still have to eye this up manually. We don't fully trust any technology to judge.
As I said, image quality has no metric that's perfect yet. So we basically run these graphs on thousands and thousands of images, like ones that we are not going to spend the time examining individually. But our job is looking at lots of pictures and judging quality. That is the only way to really do this right.
Yeah, so if we do an encoder change and we mess up, then the dots will go down, or the dots will go to the right, meaning higher bits per texel. So our goal is to push up this curve as high as we can and to the left as we can.
But you can see it's already dramatically better compression. And these are actually benchmarks from like early this year, so it's even better now. So in short, we really hope that this makes web browsers faster and better. We really hope that GPU hardware will advance more. Like, something people don't realize is that because GPUs have to support all these formats, there's a lot that they don't, like, not a lot of people target ASTC, for instance, and it's huge on the chip. Like, they could get rid of that, or they could replace it or upgrade it. If we abstract GPU formats away, they have the flexibility to create cutting-edge GPU formats without worrying about who's building encoders for these, will they be supported. No, all they need to do is write a really easy transcoder. So we're actually really excited about that. Storage sizes are crazy huge. I mean, if you think about companies like Netflix or Google or these big companies, they just have warehouses of images stored. And if we could help reduce that, it does our little part to help the environment. And advances in just streaming, maps, games, the web, virtual reality, any application that uses images can be better because of this.
Yeah,
that is
the reality
our goal.
is about 50% of the data shipped to customers is noise.
Like
if you look at the GPU texture they actually ship, we're talking games that ship hundreds, like there's games that have 100 gigs of texture data they download to customers.
This technology should have been out like
and
a long
the problem
time
was
ago.
the video card vendors deprioritized software development in general, especially tools development. So they haven't invested much in tools. So their goal was just, well, let's get the quality as high as we can and ship it and then move on.
Yeah, exactly. So that's our goal, is to, like, a lot of our job is getting people to agree with each other, and we're going to create this standard, and it's good compression too. So we're open to questions. You can ask away if you want. But thank you so much for coming.
What is your HDR support?
So right now we're making a value proposition, and that is as a trade-off. We need to get a universal format out there first that targets RGB and alpha, and then we'll look at that, at our HDR. But until we have that, like, we need a baseline, you know what I mean? So we're targeting DXT1 and ETC1S as the first, and DXT5. That's what our universal format will transcode to first.
But we have plans to do that, and it's something that's really exciting to me.
And just to note, HDR means high dynamic range,
Yes.
if you aren't familiar with that.
I mean, high quality formats in general are really important to me, like BC6H and BC7, because they're just so large now, and it prevents so many people from using them, and that's not right. We should be better than that. Go for it.
I was going to ask about MIP maps and generation of MIP maps.
Yeah.
And how does your format work with the MIP map generation?
Yeah.
I'm so glad you asked, because it's one thing we didn't have in our slides. We
kept this talk very high level because there's such a wide range of experience levels, but
texture arrays are the way you get MIP map support.
MIP maps basically are, it's like an image pyramid. So you have like the lowest level, you have a high res image, and then a level up, you have half res, and then a level up, you have a half of that, and it goes all the way down to like 4x4.
So it basically allows you, like, if you're looking at a tree in a distance, you don't need a 4K tree there. Like,
you don't need to fetch from a 4K texture. It would be very alias and very inefficient. Instead, you can fetch from, a 4x4, 8x8. And this is all done in hardware. And so what we do is we just support texture arrays. We decided we're not going to mess around with cube maps and MIP map support and all this stuff. We just support non-uniform texture arrays. So you can just give the codec, if you want thousands of frames, they can be any resolution you want, and then we compress all of that in one unit. And that's what Netflix actually does with our codec.
And the exciting part of this is it's not only supports MIP maps, cube maps, it also supports really creative uses. Like, we have people that put all their normal maps in a texture array, and it shrinks them down like crazy.
Or pre-process a video and then feed us, those
it's the basis
frames.
of a video codec, so it's really exciting.
So I'm not a graphics programmer, but you mentioned normal maps, and it strikes me that, like, compression techniques for normal maps are different from compression techniques for, like, visible photos, right?
Yeah,
so how do you judge the quality of your compression techniques for things that aren't, like, human things?
Yeah, so that's a great question. So normal maps, basically, for every texel, it's just an encoded directional vector on, like, a unit sphere. And typically what they do is they have 0, 0, 0 represented as 128, 128, 128, and then they just encode the unit vector. That way multiplying everything by 127 or 128. And so to us, it's not a photo anymore. And so the image metrics, the quality metrics that the photo people and video people use, like SSIM, just don't apply. So what we do with that, we have two things. We have MSE, which honestly I trust fairly well because I have so much experience with it in this domain. And we're experimenting with an angular metric. Honestly, MSE, that's what we use right now. And the other thing is, the real question should be, how do you fit your texture data into a GPU format? Because once it's in a GPU format, then it's compressible with our stuff. That's the real challenge. It's because our encoder actually is just a GPU encoder, GPU texture encoder. Like it's a different take on it. We recognize similar colors in the texture, similar shapes and stuff like that. I could get into details about vector quantization and all this stuff, but it's to keep things simple. That's really the hard part, is getting it into a GPU texture, and that's for normal maps. It's pretty much a solved problem at this point. But on the other side of the coin, like ETC, the format itself is designed with the human visual system in mind. It takes into account the grayscale axis, and that makes no sense from a normal map perspective. So I've made mistakes early on. I was like, oh, I should have different. What was I doing?
So we're actually one of the better codecs for normal maps for formats like ETC, because basically it's really important that this is not just used for photographs. It needs to be used for depth data, for normal maps.
Basically, when you call the encoder, you can specify the distance metric that we use.
But we can go into detail for hours.
When I first got normal map support in there, I was surprised at the things I had to do to make ETC work well with normal maps. That's what I was saying earlier.
So go for it.
So I have two kind of questions. One is, you said you use a lot of inline assembly for performance reasons, and I assume that means that you're not happy about what the compiler is doing. I'm curious, which compilers and about bugs? Or?
It was intrinsics, actually. SSE, intrinsics. So not really inline assembly so much. Like, we still let the compiler do register allocation and all that stuff. So we're not working around bugs or anything. It's just there's certain key parts of the encoder that we want to know. We want to make sure it's vectorized because it counts, But we're not talking a lot of code. It's a tiny fraction in the bigger picture.
Sure. The other question was, you said that you like OpenMP and you use it very heavily. I would love to hear more about your experience there and what implementations of OpenMP you have experience with.
Yeah.
My own has not been similar. I'm not curious.
Yeah. Well, first I use just parallel 4s pretty much. I have my own threading library like most game developers do, but so I use that and I use parallel 4s. I've read a bunch of OpenMP docs, and a lot of it was very confusing, and I've been doing this stuff for a long time. And also I was kind of doubtful about how it would be implemented, but we're using Visual Studio 2015, 2017, and GCC actually. I'm using GCC and Clang.
We like it
Linux
because it's so easy for us to drop in, and yet it works very well. So
there were some problems with OpenMP, and one problem was I wanted to have an option that allowed the caller to disable all threading, so they could do their own threading, and I found that to be a little problematic. But overall, it's been a great. To be honest, it's been a great experience. Like, our encoder consists of these massive, trivially parallelizable for loops.
Exactly.
So
we were writing our custom library for parallelization, and we discovered OpenMP.
So the open source predecessor of Basis did not use OpenMP, and I used just custom stuff, and it was a huge pain in the ass, to be honest, because I had to constantly be aware of what data to give each worker thread and stuff like that. We also have used OpenMP critical for critical sections. So those are the two main things, and I'll tell you what, the amount of value those things deliver is huge. So, and the downside is it's very ugly the way OpenMP looks in the code. So if that was standardized, that'd be great. It's not like this is a new idea.
Yeah, go for it.
Okay, I have several questions regarding the details.
Okay.
From what I understood from your slides, you do not have entropy coding done on GPU, and you rely on CPU solutions to do that?
That is correct. We've avoided the entropy coding on the GPU, and I can answer why if you're curious, but.
So basically, you encode to some blocks which are designed in a way that it should be compressible very well with general compression algorithm.
That's right. We lower the entropy or the amount of information in the output blocks. That's called rate distortion optimization. That's what we call RDO mode.
Okay, so basically what I've
That's
seen,
one possible way of using it, though.
okay, what I've seen, you're using LZ codecs mostly for that stuff. And my question is, whether do you optimize in your encoder for better compression with
Yeah.
LZ codecs?
Yeah. So Crunch supported this mode where it would output information with data with less information, but it didn't do any explicit optimizations specifically for LZ. So what it would do is it would just cut the amount of uniqueness in the data, and then we would just get lucky. It just worked. What Basis does, it takes it a step further, and it actually simulates. I've written a lot of state-of-the-art LZ codecs. I just basically brought those models into the back end of our encoder. So we actually simulate the LZ codec. We simulate the sliding dictionary. We don't actually go very far. We don't have entropy simulation yet. We just simulate the LZ part.
So that's basically something like optimal parsing.
Yes, actually, dynamic programming. Very similar to that, actually.
And one thing we've been thinking about lately is optimizing for specific codecs. Like a lot of game developers especially use Oodle and things like that. So you can send a flag saying which codec you use.
We let you change
in
the
the
dictionary
future.
size.
One more question.
Yeah.
There are some papers out about doing interleaved RANS on GPU.
Yeah.
What's your take on this?
We know Pavel at least really
We know
well.
him really
He's a
well.
good friend, and the work is really great. And it's really nice to have that in an academic paper because it kind of validates all of our work. And do you want to expand on GPU transcoding?
We're shipping. Here's the thing: we're shipping a product, and so we're very conservative. We're basically taking the min function across the whole ecosystem. And I have a lot of experience with crappy GPU drivers. And that to me is a nightmare scenario for a product.
That's actually not my question.
Okay.
I understand why you didn't do this in that product.
Yeah.
I'm asking, what's your take on that stuff, the future development?
The future. Well, I already can hear one set of game developers arguing that the GPU is busy enough. I can hear that one crowd saying that. Honestly, there are so many trade-offs in this space. For example, so the deal is with the RDO formats that we support, a lot of vendors have LZ in hardware right now. In the future, it's just going to be even more pervasive. So RDO, actually, that's one reason we do it, so that we have one format that you basically, the customer encodes a .basis. It's a relatively large file, and then they have to LZ it, compress it somewhere, and then decompress it. They can decompress it with a Hurlburt decoder, and then run a very simple shader on that to recover the GPU texture data. And in that sense, it's already completely hardware decodable. And so I think Pavel's work is great, but at the end of the day, the hardware vendors have put the stuff in silicon already, and we want to leverage that.
Yeah, I think one thing worth noting is that as we're evolving .basis, we're considering splitting this is kind of a technical detail, but we're considering splitting transcoding into two parts. The kind of Huffman decoding, and then the part that actually turns the blocks into GPU blocks. And we're working very closely with GPU hardware vendors, and they really like that idea. And so it'll be interesting to see how it evolves.
I hope we answered your question.
So, yeah.
Any more questions?
Well, you can feel free to reach us after the talk too, or email us. I mean, that email basically reaches both of us, so we'll be able to see it. And thank you so much again.